Start recording. This one. Close. Okay. Literally low. It's not in the. Jump like. See, it's not there. The light. Is it okay? Excellent. So it's recording. Okay, let's start. Good morning, everyone. I would like. Yes. What's the question? Yeah. Okay, so good morning. Today we are going to discuss about the introduction. We are going to have an introduction to the regulatory framework for the dam stability. And why is that? We have seen in recent years that there are still vulnerabilities in the maritime sector, and one of these examples, grave examples, is the accident of the Costa Concordia. These all underline the importance of having damage stability requirements and regulations which will safeguard this the safety of the passengers on board ships. So in January 9, the new harmonized probabilistic rules for dam stability became mandatory, and this initiated a new era of rule making in the maritime industry. This actually constitutes the culmination of more than 50 years of work, one of the longest gestation periods of any other safety regulation. This is actually a step change, can be characterized as a step change for in the way safety is being addressed and regulated, taking our time is justified in this case. The change from introducing the new probabilistic rules for the dam stability is also fundamental, and it has a lot of design implications, which are just beginning to register, driving home the realization that things are no longer the way they used to be. So these are some of the changes we will see come, and this is what we are going to discuss in detail today. So why damage stability and the behavior of the vessel after damage is important? Everything started with, let's say, in the last century with the Titanic, that took 2.5 hours to sink, and we all know what happened to this tragic accident. The issue was that the compartmentation of the vessel, although it was very innovative for its time being, they had some Achilles heels which actually caused the tragic outcome. This accident happened after a collision with an iceberg, and it's worth noting that by that era, the collisions which the vessels were designed for usually had the expected damages had a V shape, and this was, let's say, they were awaiting the rupture of just one transverse bulkhead. So a two-compartment damage was the typical in the previous accidents. In this case, we had the rupture of the hull for more than 4 compartments, and this caused the low sinking of the vessel. Then we had in 1956 Adria Doria, which took 11 hours to sink. This vessel capsized after a collision with Stockholm freighter, cargo ship. Then in 1982, we had the tragic accident of European Gateway, which took just 10 minutes in order to capsize after colliding with Speedling Vanguard. And this actually showed that these vessels, which they have ro-ro decks, are very prone to rapid capsize, and something has to be done in order to save people. In those cases, we need proper design because it's impossible to evacuate in 10 minutes the vessel. Then things got even worse. In 1987, we had the Herald of Free Enterprise, which from the moment water came into the car deck from the bow door to another, the vessel was intact. There was no collision, just water coming in from the bow door, which was left open, and this caused the rapid capsize of the vessel. You see here in just 90 seconds. Then, a few years later, an accident which was also very important in the safety and actually paved the way for new regulations was the Estonia. It happened in September 1994, and it took less than 15 minutes after flooding of the ro-ro deck for this vessel to capsize very rapidly. And this was done because due to the, according to the investigation, due to the heavy weather, this bow door, which you can see in this picture, was detached, and due to the construction, this caused also the ramp, which was immediately after the bow visor, to open, and the water came into the ro-ro deck, and the vessel capsized very quickly. Then we had another tragic accident 6 years later, the Express Samina in September 2000. It took 20 to 25 minutes to sink after it was it collided with a reef outside the port of Paros, and this was another accident that stressed the need for improved damage stability requirements and procedures also, because there were a lot of faults and let's say misguidance from the crew. There were a lot of problems in the way the evacuation was handled and so on. Then we have in September 2007 the Sea Diamond accident, a cruise vessel which actually collided with some rocks in the island, on the island of Santorini, and this vessel took several hours to sink. I think it was close to 11 hours. The accident happened sometime during noon, and the vessel was lost from the surface early the morning, on the morning of the next day. So this was another accident where we had total loss of the vessel. And then we come to 13th of January 2012. The Costa Concordia, also in a very similar accident with Sea Diamond, collides with some rocks, and as the outcome, you can see here there is a huge opening on the side of the vessel, and you can see that the stabilizer is actually outside. That means that the vessel was doing some maneuvers when it was maneuvering when the collision took place. This has as an outcome that the vessel starts taking water in, and slowly it capsized and grounded in its final place, where you can see here a lot of people were lost on this accident too. And this was one of, say, another link in the chain we have of accidents where we have, let's say, the incidents underlining the requirement for better dam stability requirements and better design in order to avoid the consequences of flooding. So, if we go a step back and look at the background, we see that ships, obviously, during their operation, they may suffer damage, so we cannot avoid this. This is there is a probability that some of the ships sailing out there at some point in their life will probably have some kind of a damage. Hull damages can be caused by collision, grounding, or enemy action in case of warships. The outcome of such damage would be a change of the draft, trim, and heel of the vessel. If the vessel doesn't have sufficient, and this is a key word for the regulations, sufficient stability, reserve buoyancy and stability, the damage may result to the loss of the ship. In order for the ship to survive, the vessel has to be subdivided into a number of watertight compartments. So that's the watertight compartmentation is important. Flooding of a certain number of adjacent compartments should not lead to slow sinking, as we saw in some of these examples, Titanic, Sea Diamond, or rapid capsizal of the vessel, and this is Herald, Friede, Price, and the other Estonia, which everything happened within few minutes. If we go back and see when we first understood that watertight subdivision is very important, we will go back more than 1,000 years, because the Chinese junks, which were ocean-going vessels, had already identified the need for subdivision. And we know that according to the present data, they were subdividing the vessels since the 12th century. The Great Eastern, built by the British engineer Brunel in 1858, it was advanced in many different specs, but it was not only watertight subdivided with transverse bulkhead, but it was actually constructed as a double hull. So it was much more, say, advanced in the dam stability than other ships in the same era. At the end of the 19th century in Great Britain, the Parliament chartered a bulkhead committee to investigate the impact of the transverse bulkheads, but the first shipping act, which was in 1854, 4 is the first known legal requirement addressing safety at sea concerning watertight bulkheads. In 1891, the committee, which was the bulkhead committee, proposed installation of transverse bulkheads in order to make ships longer than 425 feet, two-compartment standard. So if there was a breach, damage to one transverse bulkhead, the vessel will be still able to stay afloat. And this is the for, let's say, for historical reasons, something important. As a motive for the industry, such ships would be able to carry less lifeboats. And this was actually what triggered the Titanic tragedy, because we know that the vessel was, let's say, sinking very slowly, but the problem was that there were not enough life rafts. So this was the outcome of this legislation. The tragic loss of the Titanic in April 1912 stressed the need for international regulations for the watertight subdivision of the hull, and this was covering also the extent up to which the watertight bulkheads were extending. The problem was, if you see the black, all the sides of the vessel were painted in dark colors. And the reason for this was that these vessels were using coal as a fuel. So coaling and refueling, let's say, during the time that the vessel was in port, required the coal to be, let's say, to be transferred from openings that existed on the sides of the vessel into the stores where the coal was kept until it was used. So you can imagine if it was a white, say, a light paint outside, what the coal during coaling would cause, how dirty it would look. That's why you see that most of the vessels of that area, they were using the very dark colors for the hull. So these openings for refueling with coal were one problem for extending the transverse bulkheads to the main deck. There were other issues too. So the vertical extent of the bulkheads was an issue which proved to be critical for the Titanic accident. Then, after the accident, there was a lot of discussion and public outcry. Something had to be done, and that's why we had the first SOLAS. Well, it's let's say as a conference took place on the 20th of January 1914, and the idea was that the rules which came into force should have been applied by July 1915. The problem was that the First World War started and they stopped all the actions. And then we have the SOLAS conference in 1929, which was entered into force in 1933. And then we have due to the change, the rapid change of the technology, we had to, the ships changed actually the way they were designed. New features came into the industry, and all these the new technical developments led to the SOLAS 1948. Then we have the SOLAS 60, where also the very fast progress of the technology was captured and new requirements entered into force. And finally, we have the SOLAS 1974, which was held in London. And the amendments of the SOLAS we see now in the SOLAS, let's say, which is applicable to the ships. This is the conversion which we have now with all the amendments that took place after 1974. The Some definitions in order to understand what we are going to see. The first thing is that we are going to discuss about the floatability, which by definition is the ability of the vessel to support a given weight by means of a hydrostatic pressure acting on the water surfaces and giving rise to the buoyancy force, which is by B. Therefore, to achieve a condition of upright equilibrium, the weight and force vectors have to act along the same vertical line on the center plane of the vessel. This will give us the equilibrium. The hydrostatic stability is the ability of the vessel to return to the upright condition in still water when it is disturbed from it. This is a necessary condition. The necessary condition in order for this to happen is that the vessel has a positive metastatic height. This is depicted for naval architects as GM. And if GM is positive, it is this is the way to make sure that the vessel has the ability to return to its upright position in small angles. That's why GM positive is the small angles, the initial stability requirement. If we go to larger angles, then the vessel needs to have let's say the measure which we are using as naval architects is the writing level GZ, and its variation with increasing heel provides a better indication of the hydrostatic stability characteristics of the vessel. The regulators, based on these, let's say, requirements and these fundamentals, use the positive GM and the GZ curve to satisfy certain criteria. These include the maximum GZ value and the angle at which this occurs, the angle of balancing stability, where GZ is crossing the horizontal axis, is becoming 0 again, and the area under the GZ curve. So the GZ curve is very critical for the stability of the vessel. And if the vessel is damaged, so actually it's losing part of her internal volume and it's flooded, she will sink, keel, and trim until she reaches a condition in which the reserve buoyancy, so the buoyancy which was initially above the water line, has been brought into effect to offset the lost buoyancy which we had until the equilibrium is restored. So the buoyancy and the weight should be again equal. For the most onerous GM cases, the GM is likely to decrease and the GZ curve characteristics are likely to diminish in all regards. The vessel will capsize if GM becomes negative, so we have some inclination with the vessel upright, and there are no positive riding levels in the residual GZ curve. So GM on its own negative means that the vessel will tend to, find an equilibrium away from the upright condition. That means that if we have a crossing a GZ curve crossing again the horizontal axis at an angle of, let's say, 2-3 degrees, that means that the vessel will not have an equilibrium at 0 degrees, but it will roll between minus and plus this crossing point. So it will generally have it will be very easy for the vessel to roll, and this means that the vessel will have a tendency to increase its heel, which we don't want. The stability of the ships is, in general, is related to intact and damage stability requirements, and for the passenger vessel, this is normally assessed by their stability in the damage condition, so by their residual stability. These are the GZ cross curves which we have. We are using this more for the intact ship. The cross curves took their name by the way we are using them. So we have the various angles of inclination of the vessel. You see here different degrees: 15, 30, 45, 60, 75, and 90. And then what's happening when we have the displacement of the vessel, which we see here in the on the horizontal axis, we just cross and take the GZ curve for the various angles, and then we can let's say for this particular case, for this displacement, we can have the various values here in order to formulate the GZ curve. This is a picture where we can see the development of the different standards. You see how the first requirements for the GM started in SOLAS 1948. We had, for symmetrical flooding conditions, a GM which should be positive, and in case the vessel was let's say had a damage, in this case we wanted that the angle at which the GZ was crossing the horizontal axis should not be more than 7 degrees. So GM positive and 7 degrees is satisfied. If the GM was less than, let's say the GM was negative, it could happen if the 7 degrees rule was satisfied in some cases. If we had asymmetric condition, then we had 15 degrees as, let's say, this was the requirement for one compartment damages. If we had 2 compartment or 3 compartment damages, then we could go up to 15 degrees of heel for this inclination. There was no requirement for the area or the maximum value of the GZ phi, so it was only GM. Then we come to the 60s, the SOLAS 1960. Here we have the positive GM has a value now, so it should be 0.05, so 5 centimeters of positive GM, and the first crossing of the GZ curve should be before 7 or 15 degrees. Then we come to the SOLAS 90, which it's much closer to us, following the Herald of Free Enterprise and the other accidents. In the SOLAS 90, we have now the requirement, the GM should be positive. The vessels with 1 compartment damages should have a heel of which is not violating the 7 degrees boundary. Then we have for the 2 and 3 compartment vessels 12 degrees. And now for the first time we have a requirement for the area under the GZ curve. So the area should be more than 0.015 meters times rad, and there is a requirement also for the phi max, which should be let's say considered for the area should be less than 22 or 27 degrees depending on the sit time. And the GZ max has also a requirement, should be more than 0.1 meters. Then we go to in this SOLAS 90, which was also very important, and it raised the standard significantly from the previous damage stability requirements. We have also a requirement for the Here I need to mention that the range for the first time has to be the range of the positive stability had to be more than 15 degrees. For the intermediate stage of flooding, there is also a requirement, and in this case, it should be more than 7 degrees. The other definitions which we need to have in mind are the watertight bulkheads, the bulkhead deck, the margin line. Actually, the watertight bulkheads, as we saw, are all these boundaries that with which we subdivide the vessel, the watertight envelope of the vessel in the transverse or longitudinal direction. The bulkhead deck is the deck up to which the transverse bulkheads are extended, and the margin line, which was used during the previous deterministic regulations, is a line which is 76 millimeters below the deck outside. The floatable length is the maximum length centered at a point that can be flooded without submerging this margin line, and the volume permeability is the ratio of a compartment's volume that can be flooded very quickly. So for the watertight subdivision, we know that the vessel may sink. It's carrying more weight than her displacement, so there is no balance in the vertical direction. There is flooding to grounding, collision, enemy action, or operation system open to the sea. So if we have some switches and the valves are open and there is progressive flooding of the engine room, we may have a problem. For case when the water finds its way in, the designer has to make sure that the loss transverse stability is minimum, the damage to the cargo is minimum, the vessel has sufficient longitudinal stability, and the loss of residual buoyancy is minimum. So ideally, the vessel should sustain more and more flooding without the loss of stability until it sinks bodily by loss of its reserve buoyancy. So this is the fail-safe, let's say, case. If we cannot save the vessel, we should make certain that the vessel will not lose rapidly its stability, a capsize, because that means that the number of fatalities will increase. In order to achieve this, the ship is subdivided to a number of watertight bulkheads, so watertight compartments. So this is the ideal way of sinking. If we cannot save the vessel should go down low. For the subdivision, the bulkheads must be watertight up to the bulkhead deck and able to withstand the water pressure when they are subject to a different water line from this which you have when the vessel is intact. So if the water level in a compartment increases, then the bulkhead should have sufficient strength. Ships over certain length should have a watertight inner bottom, extending from the forward collision bulkhead up to the aft peak bulkhead. For tankers, large warships, and many rowbacks, we have in addition longitudinal bulkheads in order to minimize the transverse extent of flooding. So we have this in some vessels. We have this double hull concept, which we see here. This is now a requirement for oil carriers. So, to assess the ability of the ship to withstand the damage, a number of damage scenarios should be checked at the design stage. And for every damage condition, the naval architect is checking the waterline, the damaged waterline, the heel and trim of the vessel, and the damage stability according to the standards laid down by the rules. When the ship is damaged, the water enters, and this results, as we said, in increase in draft, change in trim, change in heel. The result of this flooding can be determined by two ways. That's what we are using in naval architecture. We have the lost buoyancy method and the added weight. The regulations usually are relying on the lost buoyancy method because this is a constant displacement method. So we assume that the vessel is losing buoyancy, but the weight stays the same. This is much easier in order to use all these non-dimensional, all these, let's say, non-dimensional indicators which we have, and also because GM is a moment, and in order to, it comes from the healing moment, the writing moment, sorry, and if we have moments, we have to divide them by a weight. If the weight changes, then we will get different numbers for the GM, and this will make things much more complicated. So we are using the lost buoyancy method. And this is a very simple example in order to understand how it works. This was first presented in the handbook of ship design, the German, der Werften, and it's also used by Watson. The starting point is the, we have a barge, and the starting point is the intact condition of the barge. We see with 0, we indicate the intact hull, and the original draft is T0. Then we have, at this draft, the volume of the barge is V0, and associated with the initial intact stability, we have the GM at this intact condition, which is by definition KB plus BM minus T. So these are the metacentric radius, the vertical center of buoyancy, and we divide here, we subtract the vertical center of gravity. After the damage, we have a hole. So this buoyancy, which existed underneath the initial draft, instantly is, let's say, is lost. So this part is not contributing to the buoyancy of the vessel anymore. So the draft have to increase. So the lost volume is K, which is the permeability times the V0, which is the volume of this compartment. The flooded compartment does not fill completely with water because the compartments usually contain equipment, furniture, structural components, or cargo, and this is why we have the permeability, which is defined by the available volume to be flooded divided by the total volume which the compartment has. Let's say, ideally, if it was say free of all these obstacles. Similarly, we have the area permeability, which we use sometimes for the waterline calculations. So if the assumption is in the calculations usually that we have a homogeneous permeability to the vessel. Let's say if we had an empty room, it will be just the walls, no obstructions there. In reality, we have the permeability of 95%, let's say, in this room, but you see that we have inside the furniture, and there is a different distribution vertically, you know, which is here. Let's say if you have a water line, which is the water steps in, the permeability of the lower spaces, the lower part of this compartment is different from the permeability we have at the upper part of the compartment. Our model suggests that we have this homogeneously, so in all the different heights or in this compartment, the permeability will be the same. The typical values you see in this table. So for a merchant ship is 95% for the compartment. The accommodation space is 95. So these are empty spaces. For the machinery spaces, typically we have 85% of the total volume to be available for flooding. The dry cargo space is 70%, bunker stores and cargo holds 60%. The final damage condition, then due to this opening, we lost some buoyancy, then the draft will increase. If we could even have some trim if this was not a, let's say, a symmetrical condition. In this case, let's assume that we have a symmetrical damage in the longitudinal direction, and this extends from one side to the other, so there is no heel and no trim. In this case, the intact draft at the final, let's say in artificial, we can have an artificial intact damage condition, which can be used for the mathematical derivations, and actually it has no meaning because this is, let's say, artificial, let's say something we need to use in order to come up with the numbers we need for the calculations. The masses are fixed. This is an assumption we have. So we have the cargo or other objects will not exit in these cases. The cargo or other objects will not float inside the room. These are assumptions which we have in the damageability calculations, and the total mass of the ship is constant. That means also that the mass distribution will be constant. So the volume, the displacement of the weight of the ship before and after the buoyancy we need in order to find an equilibrium will be exactly the same before and after the dump. And the vertical center of gravity will remain the same. So from the weight distribution, we have no changes. Let's see an example where we have a pontoon with a permeability of 100%. We have the length of the pontoon, the length of each compartment, and the initial draft T0. These are the let's say the parameters which we need. We have a central compartment damage. We lose buoyancy, where the lost volume is compensated by the increased draft. And let's see what is actually happening here. The intact stability is, if we assume these dimensions for this pontoon, we have a length of 100 meters. The length of the damaged compartment is 40 meters, the draft is 3, the beam is 20, and the assumed vertical center of gravity is 8 meters. You see that the volume, according to this dimension, is 6,000 cubic meters. The vertical center of buoyancy is located 1.5 meters above the keel, and the Dm is by definition equal to the inertia of the water plane area divided by the volume. And for a simple, let's say, these are shifted, I have to put them back. And for a simple, this simple square, let's say, this very simple geometry, this rectangle waterline, we can calculate very easily the inertia, the moment of inertia, which is L times the breadth cubed divided by 12. And then we divide this by the volume, which is very simple for this box, length times breadth times the draft. And doing this calculations, we find 11.11 meters. Then we can very easily calculate the GM, which in this case will be, with this vertical center of gravity, 4.61 meters. Then the assumption that the mass is constant, we need the same volume in order to balance the weight, and that means that the new draft here will be 5 meters. So we started with a draft of 3, and due to the lost buoyancy in the center compartment, we ended up with a new draft after damage of 5 meters. If we do the same calculations for the vessel in this damage case, we see that we do exactly the same, but now we have lost this central part, and for that reason, the new GM after damage will be just 1.17 meters. And this is a comparison. You see very quickly that the pontoon is still stable, but due to this damage, it lost almost 3.5 meters of GM. And other interesting thing is the intermediate condition, where here we have some water coming in. So we haven't lost all the buoyancy here, but there is, let's say, some part of this compartment, this damaged compartment is damaged. Here in this example, we have a height of the flood water of 1.5 meters inside the damaged compartment. And at this stage, this intermediate stage, the draft is, according to the same calculations, is 3.6 meters. Then if we do the calculations here for the various, let's say, volumes which we have, we can very easily calculate the resulting vertical center of buoyancy using the moments which we have here. We have the volume, we have the vertical volumes, the vertical moments of this volume according to the centers of have, and dividing this moment by this volume, we will find the KB, which we have, the vertical center of buoyancy, which we have in this intermediate condition. Doing the maths, we find that the GM in this, let's say the vertical center of buoyancy is 2.01 meters above keel, and substituting this value in our calculations, we will see that the GM is now only 0.68 meters. And this is, let's say, what the comparison shows, that the intact vessel started with a huge GM of 4.61 meters. The damaged one, it will end up, it will have a GM of 1.17 meters, but in the intermediate stages, we have just 0.68 meters left for the vessel. So the pontoon is still stable, but the GM is considerably lower in the final condition, and the intermediate stages can be more critical than the final. In the old days, the regulations required stability proof only in the final condition. Nowadays, it becomes much more important what happens in the intermediate stages. And something in order to break the symmetry, see what happens if the vessel has an asymmetrical damage. Then we will have change not only to the draft, but also to the trim and the heel. In this case, we see a damage which happens in a compartment which is of the say asymmetrical. It's on the port side of the vessel, and what will happen? We will lose this part, and this will cause the center of the residual water line to move to a new direction from its initial position. It will move on the other point in order to compensate for this loss. And not only this, but this asymmetry will change the main axis of the inertia, the axis with the minimum moment of inertia, and this will not longer be the symmetrical plane. So all the rotations of the vessel will be around this new axis, which will be rotated slightly to compensate for this loss. Another interesting notion is the floatable length, which is a simplified model concept which the naval actors were using when it was very difficult for the damage stability calculations to be, let's say, to be done. Everything was done by hand, and in that respect, the designers wanted to have some initial estimations of where to put the damage, the transverse bulkheads. The floatable length is something which is easy to handle. In the old days, you could do that with no computer. Nowadays, we can do it by simple spreadsheet. You don't have to use a dedicated program, although most of the programs, the architecture programs, provide facility. And the assumption is that there is constant permeability over a cross section, which often is not true. And in general, you should remember that this is only an approximation. It's a prehistoric approach, let's say, we could say, and the annual procedure is described in the Principles of Naval Architecture, the well-known PNA. And the diagrams are still popular because they provide a very good way of communicating things. And the definition of the floatable length is that this is the maximum length of a compartment having its center at this position X, which will not, if this length is damaged, will not cause the submerge of the margin line if this is a symmetrical flooding. And the margin line will show that this is a line which is located 3 inches below the deck outside. So if we do these calculations for all the different positions, we will end up with this graph where we see that if, let's say, for this for any position, we take the floatable length and we raise this, let's say, this triangle, which the height is equal to the length. If the top of this triangle, the corner here, is below this this curve, that means that when the damage happens, if we had just buckets in this and is flooded, then the vessel will not, the margin line in this damage case will not submerge. And these numbers which we have here are the different permeabilities. Obviously, the lower the permeability, the higher the floatable length curve. We actually, what we were doing, we were calculating various points, and then we were interpolating this with different methods, for instance, spline interpolation used. if we have an actual vessel, then you see that in this case there will be, according to the permeability of the various spaces, there will be different curves which can be used, stopping at its bulkhead. And what the naval architect has to make sure is that the naval architect will place the transverse bulkheads at these locations in such a way that the triangles formed here will all have the top corners below the certain curves, which are, let's say, ruling this part. So in this case, we see that if we have a two-compartment damage here with this gray triangle, the vessel, because these compartments, they have a permeability of 0.7, the vessel will have no problem. This is not the case if we had a three-compartment damage, because these triangles will meet further up, and then we will probably have an issue. We use today computer programs in order to make our life easier, and the naval architect for its damage condition specifies the hull, geometry, the mass distribution, the compartments, and the computer determines the floating position, the residual GM and freeboard for all individual compartments and groups of compartments. And often it's the applicable criteria are included in the code, so you can do an automatic search. Otherwise, the naval architect, the designer, has to check whether the criteria are fulfilled. And we have two types of criteria. We have the deterministic ones, which where we have the standard dimensions of damage are used, extending anywhere along the ship's length or between two transverse bulkheads, depending on the relevant requirements. And we have a number of standard damages which are involved single or multiple compartments to be examined. So we have predefined cases which are according to the maximum extent of damage. Each damage case is to be considered for its loading condition, and the applicable criteria are to which this case has to do with. So if we have a two-compartment damage, we will take all the two-compartment damages for this vessel, and we'll see which is the worst condition, and we will see if in this worst condition the vessel meets the criteria, then it will pass. On the other hand, of the probabilistic, we are not, we don't care for each specific condition as such. We are interested for the survival after damage, which is the measure of the ship safety, and this is referred as the attained subdivision index. The philosophy behind the probabilistic concept is that two different ships with the same attained index are equally safe, and therefore there is no need for special treatment of specific parts of the vessel, even if they are able to survive different damages. The only areas which are given special attention in the regulations are the forward and bottom regions, which are dealt with by special subdivision rules, provided for cases of ramming or ground. The probabilistic concept affords new degrees of freedom in ship subdivision and layout, but in this process, the designers are finding it rather difficult to move away from the descriptive mindset, so they have to readjust. Adapting design practice to the new freedom offered by new rules obviously requires new skills, which cannot be based on experience alone. They need to facilitate improved understanding of what this concept entails, and its limitation and range of applicability is now paramount. With the advent of the new probabilistic rules, there is a major shift in the way the naval architectures are performing the calculations for floatability and stability, and how they interpret those terms. The margin line is removed from the SOLAS 2009, which we will see later on, and the naval architect begins to delve with take into consideration the superstructure, seeking to identify and distribute the watertime spaces so that the floatability and the stability are ensured in all the extreme damage scenarios covered by the probabilistic rules. And there is consideration for the upper decks for stability needs, which lead to accounting all spaces, openings, escape routes, void spaces, and layout. And this is actually affecting the way the ship is operated. There is safety, performance, and functionality, which must be considered currently now through the routine, utilization of the optimization techniques in early design stages. And the new rules of game. So there was a discussion when the SOLAS 2009 was discussed. The requirement from IMO was that the new probabilistic concept will offer exactly the same, the equivalent safety that the SOLAS 90 was and the Stockholm Agreement in Europe was offering. And in that respect, the calibration for SOLAS 2009 has been done based on SOLAS 90, which was a deterministic concept. This calibration fueled some uncertainties concerning the derivation and the applicability of SOLAS 2009, explaining and demonstrating the relevance of each set of rules and the use of statistical damages in rule making is required. And let's say, as a principle, these shadows in how the rules are actually have been developed and what they represent, they should not exist. And in that respect, there was the intention to provide a qualitative assessment of safety. Safety index might have been enough at the time the probabilistic framework for damage stability was conceived. With the introduction of the design for safety and of the risk-based design to the maritime industry, there was a quantification of safety, which is a prerequisite, and we should treat safety now as a design objective. The level of detail in the method used is also important to quantify safety, and this carries a much bigger weight. So the new problems in the new rules is that when the main issue with the SOLAS 2009 and the probabilistic concept is how we calculate the survival factors. And this should be a consistent and accurate way. Some research work that has been done raised some concerns about the S factor, as we call it, and this, let's say, created a lot of discussion within the IMO and the international community. And in that respect, it was decided that the easy the European Commission funded project Goals was launched in September 2009 to address all these problems and explain the current pitfalls in the rules and providing a way forward of how to deal with them. And let me point here that there are some of the, let's say, critics for the criticism for SOLAS 2009 formulation is that the S factor derives from the regression analysis of only a filtered set of old cargo ships. So there was, let's say, a discussion there. And also the other thing is that nowadays we have, let's say, a lot of new ways of addressing this observability. So we can do model tests or numerical simulations, and this was not, let's say, taken into consideration when SOLAS 2009 came into force. The attendee index reflects the average survivability of the vessel following collision damage and landing in seaway, and as such, an accurate calculation of the survival probability in the probabilistic rules is of paramount importance. There is evidence that there are errors in the derivation of the survival factors, demanding a swift action by the international community, and such actions require industry-wide participation to ensure due process is followed in the revision of the rules and approved through IMO. In the meantime, the use of time domain simulation tools and physical model tests is also very important, and we will visit this in our course later on. The new damage stability standard has a statistical rather than performance-based nature and may not cater the higher level of safety expected in mega ships of today. And the FSA formal safety assessment studies that have been performed in another EU funded European Commission funded project, SAFEDOR, demonstrated the need to raise substantially the damage survivability of large passenger vessels. Equally important is the recent innovative new building projects that have shown considerable potential for rising the damage survivability standards. So it has been proven that the designers have still capabilities of increasing the safety level of the designs. And the first probabilistic concept was, let's say, proposed by Kurt Wendel back in the 60s. Then this came into force as equivalent to the deterministic with the SOLAS 974. This was done through the resolution A265. The next major step was in 1992, where for the first time probabilistic standards were applied to cargo vessels with the same principles as the 74 regulations. And then we have the probabilistic concept of survival with the harmonization of damage stability provisions in SOLAS, which we will see later on in this of lectures. The evidence, however, of this common sense driving rule making is very scarce, with accidents providing the main motivation for rule making. Emphasis has primarily been placed on reducing the consequences, that is, on the cure rather than prevention. Against this background, it's widely believed that the prevailing solution could be drastically improved through understanding of the underlying mechanism leading to vessel loss and to identification of the governing design and operation parameters to target risk reduction cost effectively. In this turn necessitates the development of appropriate methods, tools, and techniques which are capable and meaningful of addressing the physical phenomena involved. Having said this, it was not until the early 90s that the dynamic stability pertaining to ships in the damaged condition was addressed by simplified numerical models, such as numerical models of the damaged ro-ro vessel, dynamic stability and survivability, and the subject of dynamic stability in waves was, let's say, got a lot of focus after the tragic accident of Estonia, and this led to a step change as we had to incorporate dynamics, including water on deck. And then we have a number of projects, including the project Harder, which actually paved the way, and this studied the design of cargo and passenger ships and the growing appreciation of deeply embedded problems in both rules and the harmonization itself. And this dates back to the 2000 when this project took place. The overriding goal of the project was to develop a rational procedure for probabilistic damage stability assessment, addressing from first principles all relevant aspects and underlying physical phenomena for all types of ships and damage scenarios. Then it was not only Harder that was paved the way. Other projects, EU projects such as Nereus, RoRoProbe, SAFE, and SIP have another collaboration methods. IPTC has done similar work, tried to create a clearer understanding of the damage stability, and this gave, let's say, increased our confidence in the available knowledge and tools which were addressing this problem, and also gave to the designer new ways of addressing this issue. More importantly, the knowledge which we gain here passed to the regulatory instruments, and this created new and better methodologies to safeguard against design deficiencies in the first instance, until safer designs evolved to reflect these knowledge. At this point, we know that the damaged ships and waves may capsize in one of the following modes. For the high freeboard ships, we have provided that in some minimal positive rating, they have some minimum positive rating level and rates of stability. The ship will not capsize in moderate waves. Wave impacts on the side of the ship will induce some rolling in marginal stable cases, which could result in capsize at larger sea states. Often ships are more vulnerable with damage in leeward, since the GZ levels are typically less in damage direction, and the induced dynamic roll is typically somewhat greater leeward. If we have a low freeboard row ships, and the wave action gradually pumps water onto the vehicle deck, the height of the water increases, and the stability, let's say, will deteriorate, and the vessel may capsize to windward. In some rare cases, ro-ro vessels may heal leeward after the first few wave encounters, with insufficient freeboard on the weather side to prevent further water accumulation, and the ship will continue to take water on the vehicle deck until a capsize results. For the low freeboard conventional ships, this is the typical mechanism of capsize for non-ro-ro ships. The highest waves will fall boarding seas, and they will be piled up on the windward side of the deck, inducing roll and capsize usually to the windward. The vessel, the weather deck, tends to drain quickly if there is no capsize and there is no build-up or accumulation of water as seen in the closed ro-ro decks. One or two high waves in close succession are often sufficient to cause the capsize. The mechanism for the capsizal of cruise vessels is slightly different. Here we have the multi-free surface effect. Then, because they are very, let's say, densely subdivided, then we have different levels and different the water coming in will form different. Will go into different compartments, and we will have free surface effects, which will deteriorate, reduce the stability, and eventually leads to rapid capsize at any stage of flooding. This is the available regulatory instruments we have. In SOLAS 74, we had the in-one compartment standard. That means that the vessel was, let's say, safe from sinking or capsizing if one compartment was breached. Then we have in SOLAS 90 the two-compartment standard, and this was proof that the vessel will be able to, let's say, withstand even sea states up to approximately 3 meters for ro-ro vessels. And then we have the Stockholm Agreement when we made sure that the vessels will be able to operate even at 4 meters significant wave height, existing at the time of the incident. And they harmonized then SOLAS 2009, the probabilistic concept, which is equivalent to SOLAS 9. For the SOLAS 90, we will discuss later on more details, so we will not get into more details right now. Thank you for your attention. Any questions? Any questions from our audience online? Okay. Yeah. Okay.